Welcome to another deep dive, listeners. Today we're going to explore, I think, a pretty interesting technique in machine learning called knowledge distillation.
It's a fascinating area. It's basically finding a way to make our models smarter but also more efficient.
Oh, okay.
Yeah, it's kind of like if you think about like transferring the skills of a master chef, to like a culinary
Yeah, that's
student.
that, yeah.
Yeah, you're trying to impart that knowledge.
Okay, and we have a paper today,
We do.
and it is called Distilling the Knowledge in a Neural Network. And this is by Jeffrey Hinton and some colleagues.
Yeah, Hinton's like a real pioneer in this field of deep learning, so
Okay,
we're definitely in good hands with this paper.
all right. So to kind of set the stage here, we often have these large, complex models, and they're incredibly accurate,
Right?
but they can also be very computationally expensive.
Yeah, exactly. You can think of it like a gourmet meal. It has tons of ingredients and all these intricate steps.
Okay.
It's delicious, but it's not something you can whip up every day, right? Yeah.
That makes sense.
Yeah, and then you have these, smaller models that are
Right.
much easier to use, especially if you're thinking about deploying on something like a smartphone, for example.
Right, yeah.
But they might not be quite as accurate. And so the goal of knowledge distillation is to kind of bridge this gap
Okay.
to get the knowledge from that big complex model into something smaller. So it's almost like taking that really complex dish and just getting it down to a single perfect bite.
I like that.
Yeah.
Okay, so now how do we actually do this? How do we actually transfer that knowledge?
Right.
And the paper introduces this idea of using what they call soft targets.
Yes.
Can you explain what that means?
Yeah. So traditionally, when you're training a smaller model, you're giving it just the hard label. So, cat or dog.
Right.
But what we're doing here is we're actually using the predictions of the large model as the training data for the smaller model.
Oh, okay.
So instead of getting that sort of definite cat or dog, it's getting a probability distribution over the classes.
Interesting.
Yeah, so it's almost like, think of it like if you're trying to learn to identify birds, like a hard target would just tell you that's a robin, but a soft target would be like 80% robin, 15% sparrow, 5% cardinal.
So it's giving the student model, I guess, more information to learn from.
Exactly, it's giving it more nuances,
Right.
and it's allowing it to learn to understand these kind of more subtle relationships,
Right, sure.
even for classes that it might not have even seen examples of when it was being trained.
Okay, and so they highlight this in the paper with some experiments on what's called the MEOF data set.
Yes.
And this is a pretty classic benchmark for handwritten digit recognition.
Right, yeah. It's like the hello world of image classification. So
Mhm.
everyone starts with MNIST.
And so what they found, and this is pretty surprising, they found that even when the smaller model had never been shown an example of, say, the digit 3 during training, it could still classify it correctly.
Yes. Isn't that fascinating? So somehow it was able to pick up on these relationships between the digits
Right,
that
yeah.
were embedded in those soft targets, even though it had never seen, every possible way that a 3 could be written.
That's amazing. That's really cool.
It is. It is.
Okay, so now they take this concept and they apply it to, I guess, a more real-world problem, which is acoustic models for speech recognition.
Yeah. So now instead of handwritten digits, we're talking about understanding spoken words,
Yeah.
which is obviously a very challenging problem.
Yeah, okay. And so,
So they started off with a very powerful baseline model, and they talk about this in section 4.
okay.
And this was trained on a very, very large data set of spoken English.
Okay, so they have this big, powerful speech recognition model. What's the next step?
So then what they did was they actually trained an ensemble of 10 of these models.
Oh,
10 of these models all working together, which you can imagine is going to be even better than just one, right?
Yeah, but then it would also be, I imagine, computationally very expensive.
Right. Exactly. So that's where the distillation comes in. So what they did then was they distilled this ensemble
Okay.
into a single model. And this model actually had the same architecture as the initial one.
Interesting. Okay, and so how did this distilled model perform?
It did really well. You can actually see in table 1, if you look at the results there, it gave almost the same accuracy as that big ensemble,
Wow.
both in terms of frame classification accuracy and what's called word error rate.
Okay, so we're getting close to the performance of 10 models
Yes,
with the efficiency of just one.
exactly.
Right.
It's really quite remarkable.
That's really impressive.
And it really shows the power of this technique, especially when you think about, like, deploying speech recognition on, devices where you might not have a ton of compute power.
Right, like your phone.
Exactly.
Right, okay. So now things get even more interesting when we start dealing with really massive data sets.
Mm.
And the authors introduced this idea of something called specialist models.
Right.
So can you walk me through what's the idea behind that?
Sure, yeah. So, imagine you're working with a data set like what's called JFT, which has, millions and millions of images, thousands of categories.
Hmm.
Even training a single, like, large model on something like that can be incredibly
Resource intensive.
resource intensive,
Oh,
exactly.
right.
So this is where these specialist models come in. So instead of having this one model that's trying to learn everything, about every class,
Right.
it's like, okay, let's have models that specialize in specific things.
So like instead of one giant, you know, master chef, we now have a team of specialists, each kind of focusing on their own, area of expertise.
Yeah, exactly. So it's like, you have different chefs that might specialize in different types of cuisine,
Okay.
right? And so each one is focusing on a smaller subset of the data so they can become really, really good at that.
Gotcha. So, okay, now how do we decide what each specialist focuses on?
Right. Well, that's a great question. It's not like we can just go in and be like, okay, you're going to specialize in this, you're going to specialize in that, right?
Right.
So they actually used a very clever technique based on the predictions of the generalist model.
Okay.
So they actually clustered the classes together based on the covariance matrix of the model's predictions. So essentially, they're saying, okay, if the model is often predicting these two classes together, those probably should be grouped.
Okay, so the model is kind of telling us what it finds tricky,
Yeah.
and then those become the domains for the specialists.
Exactly. So it's like letting the model kind of dictate a little bit,
Right.
what needs more attention.
Yeah.
And so if you actually look at, I think it's table 2 in the paper, they show some of the clusters that they came up with,
Oh,
which are actually quite interesting. So, for example, one cluster was things like tea party, Easter, bridal shower, baby shower, Easter bunny. And then another one had all these different types of bridges, like bridge, cable-stayed bridge, suspension bridge, viaduct.
I can see how those would be.
Yeah.
Like even for humans.
Yeah, even for humans, those can be kind of tricky. So
Yeah.
the idea is, if each specialist is just focusing on a smaller number of classes, they can become really good at, teasing those apart.
Okay.
And plus, the nice thing is, all these specialists can be trained independently,
Right.
and they can actually be trained in parallel, so you can really speed up this whole process.
All right. So we had this, team of specialists. They're all trained on their own little niche.
Right.
How do we actually use them to make predictions?
Okay, so good question. So they use kind of a two-step process. So first, you run the generalist model, just like you would normally. And that gives you a prediction, right? So, it might say, okay, I think these are the 5 most likely classes for this image.
So it's kind of like, I don't know, like a triage nurse,
Yeah, exactly.
kind of narrowing down the possibilities.
Right, just narrowing down the possibilities. And then any specialist models that have expertise in those top predictions, those are the ones that get activated.
Okay.
And so their predictions are combined with the generalist prediction to get kind of this final refined output.
So it's like now we're calling in like the specialized doctors based on
Exactly.
whatever the initial,
Yeah, like the initial diagnosis.
Right, yeah. And so how did this approach actually work?
It worked really, really well. You can see in table 3, they show the results on this JFT data set.
Okay.
And they found that just adding 61 specialist models actually led to like a 4.4% relative improvement in top 1 test accuracy compared to just using the generalist model by itself.
Ah.
So a significant boost.
Yeah.
And they found this really interesting trend that the more specialists that covered a particular class, the larger the improvement tended to be. Which kind of makes sense, right? Like,
Yeah.
the more expert perspectives you have on something, the better you're going to understand it.
Yeah. The more experts you have in the room,
Exactly.
the better the results are going to be.
Right. And plus, remember, all these specialists, they can train much, much faster than that big generalist model.
Right.
And they can be trained in parallel. So the whole thing becomes a lot more efficient.
Okay, so I've got this really cool technique for transferring knowledge from large models to smaller ones. We can even scale it up with these specialized models.
Yeah.
But before we get, too carried away, we have to talk about a very common issue in machine learning, which is this idea of overfitting.
Right. Overfitting is always a concern, especially when you're dealing with smaller models.
Yeah, it's like if you have a recipe that works perfectly with those specific ingredients, but if you change anything,
Right.
it all falls apart.
Yeah, exactly. So they actually did this very interesting experiment where they trained their baseline speech model on only 3% of the data.
Oh, wow.
Yeah, it's in table 5.
So they're really limiting
Yeah, they're really limiting it.
the amount of data the model has access to.
Exactly, yeah.
Okay.
So when they trained it on just that 3% of the data using the hard targets, it severely overfit, which is not surprising.
Right.
But when they used soft targets from the full model, but still on that same, limited data, the results were really astonishing.
Okay, so what happened? Like how?
So basically, the model that was trained with the soft targets was almost as good as the model that was trained on the full data set,
Wow.
even though it had only seen 3% of the data. So somehow those soft targets were acting as this really powerful form of regularization.
It's like the smaller model is picking up on things that even the big model
I know, right?
maybe even misses.
It's really quite amazing.
Yeah, that's really cool. So it's almost like instead of just memorizing specific examples, it's learning a much more general understanding of the data.
Yeah, exactly. It's like it's understanding the underlying structure
Right.
rather than just memorizing these specific details.
That's really fascinating.
Yeah, and this has some really interesting implications for when we're thinking about using those soft targets with the specialist models we were talking about earlier.
Okay, so tell me more about this. I want to hear more.
Yeah, so, imagine training these specialist models, but using the soft targets from that generalist model to help prevent them from overfitting.
That's really interesting. So we're using the knowledge of that larger model to make these smaller models
Yeah,
more accurate.
exactly. And even more robust, to make sure they generalize well.
Yeah, okay. So this whole concept of specialist kind of reminds me of another technique I've heard about called mixture of experts.
Right, yeah, mixture of experts, that's a good one.
Yeah.
Yeah, they are similar in that you have multiple expert networks, and each one is specializing in a different part of the data.
Yeah, it's like having a team of doctors, each specializing in a different, I don't know, organ system or something.
Yeah, that's a great analogy. But there are some key differences.
Oh, okay.
Yeah, so in mixture of experts models, you have this separate network. It's called a gating network, and it decides which expert to trust for a given input.
Okay.
And all those components, the experts and the gating network, they're all trained together.
Oh, so it's like a much more integrated system.
Exactly. Yeah, everything is learning at the same time. Whereas in this distillation approach, we're using a kind of fixed strategy based on that generalist model's predictions. And the specialist can be trained independently
Right.
and even in parallel, which can be a big advantage.
Yeah, especially when we're talking about these huge data sets like the JFT data set.
Oh, yeah, absolutely. When you have millions of images, being able to train those specialists independently is a huge, huge time saver.
Yeah, that makes sense. Okay, so before we wrap up on this paper, I wanted to touch on one point they make about the objective function that you use for training.
Right. Yeah, they make a good point there. They argue that when you're distilling knowledge, the real goal shouldn't just be fitting the training data perfectly,
Right.
but it should be to generalize well to new data.
Right, because ultimately we want these models to work in the real world.
Exactly. And by using those soft targets from that bigger model, we're essentially teaching the smaller model to generalize in the same way.
So it's like the large model is saying, hey, you should be paying attention to these subtle patterns,
Right.
even if they don't always lead to the exact right answer on the training set.
Yeah. Yeah. It's all about capturing that underlying structure in the data, not just memorizing specific examples.
Yeah, and this seems especially important when we only have limited training data, like in that example with the speech model.
Right. It's trained on just 3% of the data.
Right.
But the model trained with those soft targets did almost as well as the one trained on the whole data set.
That's incredible.
It's really quite remarkable.
So those soft targets really act as a guide
They do.
to prevent the smaller model from overfitting.
Yeah, it's like they're giving it just enough information to learn the right things, but not so much that it gets bogged down in the details.
Yeah. Okay, this has been a really fascinating dive into knowledge distillation.
It has.
We've learned how to take knowledge from these large, complex models, put it into smaller, more efficient ones,
Right.
and we've seen how this technique can be applied to all sorts of things,
Yeah, all kinds of things.
like digit recognition to speech recognition.
Absolutely. It's a very versatile technique.
Yeah, and we talked about how using those soft targets can be a really powerful way to prevent overfitting, especially when you don't have a lot of data to work with.
Right. It's a great way to improve the robustness of your models.
Yeah, and then we talked about these specialist models.
Yeah, these specialists are really fascinating. It allows us to deal with these really, really massive data sets with like millions of images, thousands of categories.
Oh,
It's
yeah.
a way to scale things up, make it all more manageable.
Yeah, this knowledge distillation is a really powerful technique, and it really seems like it has the potential to, really change how we build and deploy these machine learning models.
Yeah, absolutely. I think it's going to have a huge impact in the coming years.
Yeah, okay. So before we wrap up completely, I want to leave our listeners with kind of a thought-provoking question.
Okay, I like it. Yeah.
If we can distill knowledge
Mhm.
between these artificial neural networks,
Right.
could we apply similar principles to transfer skills or expertise between humans, you know?
Hmm. That's a really interesting question. It makes you think about the nature of knowledge and how it's passed on, whether it's
Mm.
between machines or between people.
Yeah, maybe there are like these hidden soft targets in human learning that we haven't really discovered yet.
Right. Yeah. Or maybe there are ways to make learning more efficient and effective
Right.
by sharing not just the hard facts, but also the insights and intuition that go along with them.
Yeah, I think that's a great point. It's something to think about for sure.
It's a fascinating area to explore,
It is.
kind of bridging the gap between machine learning and human cognition.
Exactly.
It's a reminder that by studying artificial intelligence, we can learn a lot about ourselves.
Yeah, for sure. Well, on that note, I think we've reached the end of our deep dive into knowledge distillation.
It's been a great discussion.
Yes, it has.
I've really enjoyed it.
Me too. And a big thank you to our listeners for joining us on this journey.
Yes, thank you for listening.
We hope you found it as fascinating as we did,
Absolutely.
and we'll see you on the next deep dive.
It really makes you wonder if there are better ways to teach and learn,
Yeah.
than just the traditional ways we've always done it.
Yeah, maybe we can learn something from these, machine learning techniques and apply it to education.
Right, exactly. And this whole idea of temperature and distillation, I think, is really interesting too.
Oh, yeah. Tell me more about that.
So remember how to use that temperature parameter in the softmax function?
Hmm.
And that kind of controls how soft the probability distribution is?
Right. So like a higher temperature would make the probabilities more spread out,
Yeah,
and
exactly.
a lower temperature would make them more concentrated.
Exactly. And they found that actually adjusting this temperature can improve the performance of the distillation.
Oh, wow. That's interesting. So it's like we can fine tune how much uncertainty we transfer over
Yeah, it's like finding that sweet spot.
from the big model to the small one.
Yeah, exactly. So, maybe there's an optimal level of conceptual softness for different stages of human learning too.
Yeah, I like that. So, maybe in the early stages, it's better to have a broader understanding. And then as you learn more, you can kind of refine that knowledge and become more, specialized, like those specialist models.
Exactly. Yeah, it's like learning to cook, right?
Yeah.
You start with a simple recipe just to get the basics down,
Uh-huh.
and then as you get better, you can start experimenting, trying new things, and developing a deeper understanding.
And maybe, having a good mentor
Mm.
is kind of like providing those soft targets in a way.
Yeah, that's a great analogy. They can guide you, but they don't give you all the answers right away.
Yeah, you got to figure some things out on your own. Well, this has been, I think, a really interesting conversation.
It has. It's been fun.
Yeah, it has. And a big thanks to our listeners for joining us on this deep dive into knowledge distillation.
Yes. Thank you all for listening.
We hope you learned something new and
I
interesting.
hope so too.
And yeah, until next time, keep those minds curious and stay tuned for more deep dives into the world of research. We'll see you then.